Yes, okay.
Well, hello. Is it okay?
Okay.
Okay,
So
thank
please
you.
begin. Please begin.
Well, first of all, I would like to say that I'm happy to meet again with my friends and colleagues. Unfortunately, it is very pity that we cannot meet in person, but I hope very much that the next year we will meet again in this to celebrate this date of Leonid Pavlovich Shilnikov. I would like to present here some new work in collaboration with two my colleagues about nonlinear modes for nonlinear Schrödinger equation with complex potential. First of all, I will have to explain why this problem merits to be studied. So, if we consider the nonlinear Schrödinger equation without a third term that is here, it is a well-studied equation, and there is a lot of results about it. But in some applications, recent applications, it is necessary to include the potential term, non-autonomous term. This occurs at least in two applications, two theories. And one of them is the theory of Bose-Einstein condensation. And the second is the nonlinear optics. In the first context, it is related to the trap potential. This W is a trap potential that confines the condensate. And the second is, it describes the profile of waveguide. So we have to introduce non-autonomity into nonlinear Schrödinger equation. Now, the next step is to consider the basic objects in this model that are nonlinear stationary states. They correspond to this ansatz. And for the function phi, the equation appears as follows. So this is the second order non-autonomous equation and nonlinear of course equation. And we are interested in localized solutions. In some applications, they call soliton solution. Not in the sense of soliton as completely integrable solutions of completely integrable mode, but in the sense that it is localized only. We can characterize these solutions by some value, some no, and address the following questions. Here we have additional parameter that correspond to the internal parameter in context of initial equation. So it is a real parameter. It is important that it's a real parameter due to some physical considerations. And the question is whether there exist the families of solutions of this equation. Family means that these solutions, this branch of solutions, are parameterized by this parameter mu. This question is important due to the following consideration. Typically, only solutions, only modes that are included in these branches are stable. Typically, the solutions that exist only for some fixed value of mu are unstable. Well, it is not a theorem, but typically it is. So the question now we go to some previous results to look at some previous results. For example, if the potential W is real, it is known that there exist such modes, such families, and some of them are shown here. For example, for potential in form of quadratic well, when W x is x squared, there exists such potentials, such branches, and they are shown on these diagrams. We can draw them putting on some on horizontal axis mu and on another axis, vertical axis, n, the norm of the solution, and they differ in shape. So there are such families. However, if we consider complex potential, there are some problems in with these families. It is known two cases when these families do exist. So one of them is PT symmetric potential. This means that the real part and imaginary part of this potential are related as follows. The second class is so-called Vadati potential. And here, real part and imaginary part are related through some additional function, W small, that due to some hidden symmetry allow for these families of solutions. This is quite recent result, in fact. It is about 5 years ago. Well, and the question about other cases when this equation, this complex potential admits these families is open. So recently, it was suggested that to consider some specific class of potentials. We call in this study these potentials VDV potentials. Why VDV? VDV due to the fact that in this potential, real and imaginary parts are proportional as follows. Imaginary part, derivative on imaginary part is proportional to real part. So this is why we call this VDV potentials. It was the name is what's suggested in our paper, but initially it was suggested to consider these potentials in a paper of Yanis Kouminis and co-authors in a recent paper in House Electrons and Fractals. Here the coefficient is arbitrary real, and the function W1 is arbitrary real valued and bounded function. How authors of this paper found this class? To simplify the consideration, it was done as follows. Consider our equation for nonlinear modes with small potential. Here, epsilon is small. When epsilon is 0, we return to Dufink equation, and it has a well-known second shape solution. Here, in this equation, if we have no potential, the point where we can place this on the real line, where we can place this localized mode is arbitrary due to translation invariation. However, if we switch on epsilon, even small, this point where we have to put this potential, if this solution exists, in fact, depends on this potential. And the authors of the paper, Kominis, found that this point x0, for this point, there are two equations that, in principle, can contradict each other. But in the case of VDV potential, they these conditions coincide. And this condition is like this. So from this condition, we can found x0, and then they concluded that these solutions exist, and in fact, in this case, if it is a situation of general position, can be included into this families. So we take some mu. We found that conditions for existence of localized mode fulfill. So we say that it is possibility to have these branches of solutions, families of solutions. We decided to study in more detail this situation, because our previous experience showed that no solutions should be here. The situation turned out to be very interesting, in fact, and I will show what it was. We considered the VDV potential well of finite depth. So the idea was to consider both numerically and analytically the situation when the potential is VDV potential, but it is not PT-symmetric potential and not Vadati potential. For a study, we considered specific class of potential. It is a non-symmetric potential in the sense of, for example, PT symmetry. And we make some general consideration and then compute to found or to exclude the situation when this solution can exist. I will explain now. The question typically is, how can we show by numerical computation that solution do not exist? I will try to explain. So the idea is as follows. I will think about the problem as a problem of shooting and try to find the solutions by shooting method. So denote S plus the class of solutions for the equation we consider that tend to 0 when x tends to plus infinity. So in this case, these solutions has asymptotic behavior like this, where C plus is a complex constant. Well, in fact, we can prove also that for any complex constant C plus, there exists solution of a class S plus. Similarly, we can consider S minus the class of solutions that tends to 0 when x tends to minus infinity. And in this case, we have a similar situation for the constant with the constant c minus, and here p plus is proportional to decaying and minus infinity exponent. Well, of course, it is quite natural since the potential tends to 0 when x tends to plus and minus infinity. So the dominated term is this. It is exponential decay. So of course, it is quite natural. Okay. Now the question is to found these constants and then to organize the fitting of two half trajectories in this case. Now let's compute how many conditions we have here for this. Well, we have two complex constants, and so there are four real parameters. However, an important peculiarity of this equation is that it is invariant with respect to phase rotation. So this transformation transforms solution into solution, of course. So we can do the following. We assume that C plus and C minus are real, but introduce arbitrary phase that transforms solution into solution. So in total, there are three real parameters. It is C plus, C minus, and arbitrary phase theta. Now let's compute how many solutions, how many equations we can have here. Matching conditions. The matching conditions are four. The solution from the left and the solution from the right should have the same modulus, and argument of these solutions should be different. Should differ by the same angle theta. But we have only three parameters that can that should allow us to solve this system. So how we can show that, that this situation really appears? Now we have to compute the problem to solve numerically. Well, this is the picture how it works. We have two half trajectories that should be matched. The conditions in zero should be matched to each other. Should match each other. The idea is as follows. First of all, we want to compute the values C plus and C minus that are real in such a way that the modulus of half trajectory from the left and half trajectory from the right for the function and for derivative be the same. We do the following. We compute half trajectories, and we can see that the values, these values from the left and from the right, depends on the parameters C plus and C minus. So we can draw on the plane. Where is it? No, we can draw. No, sorry. We can draw two curves on the plane R great and R small. So we have some curve dependent on C plus. Here is R and R small. and the curve that is parameterized by sigma. And in the point of the intersection, we will have equality of the modulus, the function and the derivative. And now we have to check whether the angle theta is the same for the function and for the derivative. Well, we consider this difference, and theta is the angle, the difference of angle of arguments of theta plus and theta minus, and theta tilde is the difference of arguments of theta x derivative and theta minus from the left and from the right. So the condition for solvability that they coincide, we introduce delta, that is should be 0 if the solution exists. So if delta is 0, we say that we have nonlinear modes. It is true solution of our equation. If delta is small, we will say that we have pseudo modes. It is nothing from mathematical viewpoint, but it is maybe important from physical viewpoint. It is nearly solution that can be observed in some applications. So some idea, some theory about pseudo modes was developed, not considered only as modes, or spherically modes, was developed by the team of Kominis and co-authors. They observed in numerics these pseudo modes, and they concluded that they do exist. However, we perform numerical study in this case. So, first of all, we found these modes, these pseudo modes. The first step was to consider intersections of these curves, as I said, to find the point of intersection, and then to check whether the value of delta is 0. Node is not 0. It can be small if epsilon is small, but it is not 0. However, it is interesting that, first of all, if we say that the parameter, introduce one more parameter that is epsilon, that corresponds to the strength of potential. Well, we have epsilon multiplied by W, this potential. So if we take it as additional parameter, we will find true nonlinear modes. So they are isolated. They exist only for specific values of epsilon. So from mathematical viewpoint, no branches of solutions exist, but there exist points, specific values of epsilon where these solutions exist. However, they are unstable. It is not, they are not interesting from physical viewpoint. On the other side, if we consider these pseudo modes, when epsilon is small, they are not solutions. They are pseudo modes. However, they are quite robust in numerics. You can see here that how they propagate. Well, they are quite, for epsilon small, they are quite robust. And they oscillate around the coordinate predicted exactly by this analysis of Kominis. And so to conclude, the class of VDV potentials is really interesting. It was introduced by the team of Kominis and his co-authors. So, but the objects that are described are not exactly solutions. There exist really solutions, but they do not form the branches. They isolated solutions and they are unstable. However, these pseudomodes do exist in numerics, at least they are long-lived, and maybe quite prominent. So that's all. Thank you very much.
So let us thank the speaker, and maybe one question or two.
Sorry, could you repeat, please? What are pseudomodes? Because I somehow blinked and.
The modes. Well, well, just a moment. Pseudomode means that it is not exact solution of. Also, just a moment.
They're like finite solutions for finite x, or
Well, let me say as follows. We have this solution, this equation, and this satisfies this equation up to order epsilon square in our study.
I see. Okay, good. I got it. Okay.
It is not exact solution.
Okay, thank you. I got it.
So thank you once again.